Okay, so it's time to start, and I just want to let you know that the homework 13 that's due Friday is posted now, and it's going to cover exactly what we're doing today. So by the end of lecture today, you'll be able to finish the homework for this week. And that also, if you haven't tried it yet, here's the second R bonus is up, and I encourage you to pick up your exams, or if I have your error sheets too, so come anytime during office hours. They'll be there throughout the semester, so anytime you want, you can pick up your exam. So now let's remember where we left off before, and let's go over to the document camera here, and we're on page 128, and what we're doing is analysis of variance for just simple regression. We're starting off with just one slope, one x predicting y, but we're using this method, this general method, that's going to allow us to add additional predictor variables, additional x's. So that's what, and I just wanted to illustrate it graphically for you with just one x predicting a y, and we just did it with three simple points here. And remember what we're doing. We're breaking down the total variability of the y variables right here, so just the 3 points, into two parts. One part that's due to our model, which is just this right here. Our model is just, that's our model. It's just a regression line. So that's what we're predicting these y's from this regression line right here. And so we're predicting, so you have this total variability. Here's a y point, and how much its variability is just how much it deviates from its mean. We're breaking it up into two parts. The part that's predicted by our regression line here. So we predicted these three values right here with this regression line. And then the part that's left over in the errors. That's just our observed y minus our predicted. And we did it for each of these points, and I think I did it wrong for this point here. At least it looks wrong here. So we want the model, which is right here, the sum of squares model, is how far the prediction is from the average, how much better we're doing than just predicting the average. So this should have gone all the way up here, like that. And then our error part is just the observed minus the predicted. So it's this little bit here for this one. Okay, so we're taking this whole thing, this whole green thing, like this whole thing, and breaking it up into two parts. The part that's the model and the part that's the error. This one's the easiest to see. Here, look, we have all error. No model, 0 here, etc. All right, so that's what we did last time. And we just had 3 points, so we did it for just, here we had just n equals 3. So we just had those 3 points, n equals 3. And that's just our points in our sample, 3 points. And then we say we have two parameters right here. Okay, so P is equal to 2. It's 2 parameters in our model. The parameters, remember what they are. They're the population parameters we're trying to estimate with our sample stats, our sample statistics. All right, and why do we just have 2 here? Because we're estimating 2 betas here. You know, we just have these 2 betas, the Greek letters, right? We're estimating them. What are they? There's one intercept, 2 betas, beta 0 and beta 1. And so we're just estimating an intercept and a slope. And we're going to add more slopes later on, beta 2, etc. So we just have 2 parameters now. And we filled out this analysis of variance table here, showing you how we break down the total sum of squares total, that we figured it out here. We said, all right, the 8 plus 6 is going to equal 14 here. So we just broke down the variance of the y's into two parts. That's all. All right, and then we saw how the degrees of freedom also sum. That the degrees of freedom for the model right here is n minus 1, and this is for the total is n minus 1, and we broke it up into two pieces, p minus 1 and n minus p, and they sum as well. And then we saw that we're going to get this statistic, this F statistic, that's going to be our test statistic for just like we did with a T and a Z, but now this is going to be our test statistic for multiple regression. But we can use it for simple regression, and I'm going to show you how it's the same thing as that if you squared the T, you'd get the F statistic. And it's the ratio of their sum of squares model to the sum of squares error after you divide through by their degrees of freedom. So that's what we did, and let's just do it. This was just with 3 points. Now we're going to do the same thing with an example that we already worked out before. And this is the same example that we looked at on drinking and GPA, the same one we saw on page 123, where we got this. The idea was here, we thought, okay, we want to see if there's some negative correlation in the population between how much people drink and what their GPA is. So we sampled 25 people from all U of I students for this hypothetical data. And in our sample, we got this correlation right here of negative 0.2. I'm just writing it bigger here so you can see it. And we wanted to know whether that correlation, that's a pretty small correlation, and we wanted to see whether it would hold up, in our general population, or whether this is just due to sampling variation. If we took another 25 points, we'll get something different, right? So we already did the t-test on this. But now I'm going to show you how you can do the same thing using the f-test. All right? So we're going to use it. We're going to, remember, we're going to relate it to r squared. The correlation right here, it's helpful to think of ANOVA in terms of that r squared, which is the coefficient of determination. Remember, we talked about it before. We said that the r squared is the proportion of the total variation of the y's that's due to our model, and 1 minus r squared was what's left in the errors. We talked about this before with little r squared. And big R squared is really little r squared is is a special case of big R squared. This is the correlation coefficient, a more general correlation coefficient. All right, so what am I saying here? So what have we done? We said SST, right? SST is equal to sum of squares model plus the sum of squares error. And all I'm saying is that this part right here, this is the same thing as what? You have the total variation, and you're breaking it into two parts. R squared times SST is the part that's the part that's explained by our model, plus 1 minus R squared times SST is the part that is explained by our errors. Remember, if we took the square root of that, we'd get the square root of 1 minus r squared times, and then divide through by n by the standard deviation of the y's. This is all we're doing. It's what we've had before. Okay, so so this is going to come in very useful. I'll show you why. So let's do the same example here. Now, so here's our model, right? So you can think of this as right here, r squared times SST. And this is 1 minus r squared times SST, and it adds up to the total. So If we have r here, and we square it, we'll get 0.04. And if we know right here, this is what are we predicting from what? We're predicting GPA from drinks. So this is X and this is Y. So we know the sample standard deviation. And remember, if we square that, we'll get the variance, right? This is the standard deviation. Do you notice how the numerator here under the square root sign is just SST? If you divide by n, you get the variance, and you take the square root, you get the standard deviation. So if we square this, we'll get the variance. So we'll square that. And then this part, so now we have the sum of squares divided by n, that's the average, then just multiply through by n. So this is the same thing as n times sdy squared. It's just n times the variance. Divide by this by n, you get the variance. Take the square root, you get the standard deviation. So now, if we do that, what is n? So all we're using is this and this right now. Okay? And so then we'll get 25 times that. And that's 6.25, which is our sum of squares total. So we can put that right there. Okay, so now we can fill out the table here. And let's do that. So how does this 625 break down? This is the variation of the variability of the y's, and we're going to multiply, due to the model, we'll just multiply that by r squared. So we'll say 0.04 times 6.25. And we'll multiply this by 0.96. 1 minus r squared. R squared is 0.04, so 1 minus r squared is 0.96. So 0.96 times 6.25. And that is 6, and that's 0.25. So that's how that breaks down. They add up to 6.25. So now we're going to divide by their degrees of freedom, and remember what those are. So altogether, the degrees of freedom is n minus 1. So that's just 25 minus 1, which is 24. And then for the model, it's p minus, there's two parameters to the model right here. So it's p minus 1. So that's 2 minus 1, which is equal to 1 degree of freedom for the model, and n minus p for the errors. P minus 1 and n minus p add up to n minus 1. P minus 1 now, right? So this is just 25 minus 2, and that's 23, and they add up. All right, so now what are we going to do here? So we're just going to take our mean, this is just the mean square, which is just the sum of squares divided by their degrees of freedom. So for the numerator, the mean square is what? For the model is 0.25 just divided by 1. And for the errors, it's 6 divided by 23. So this is just, all right, 0.261. And then this F ratio is just the ratio of the mean square model to the mean square error. So our F statistic is 0.25 divided by 0.261, which is about 0.96, almost 1. All right, so that's our F stat. Now, so we're going to use this statistic to test right here, to test the null, which is at the slope 0. that there's no correlation. That's equivalent to saying there's no correlation between drinking and GPA, against the alternative, which is two-sided always, because think of it, we're doing squares here. F has to be positive. We're looking at all these, we're doing the sum of squares. So it's always positive. So it's always two-sided. It can't distinguish between less than, your alternative being less than 0 and greater than 0. So it's putting those two together. And we're going to do the same thing we did before. We're going to say, suppose there is no correlation. How likely would you be to get a sample slope as far away from 0 as we got, which was the sample slope was a negative. The correlation was negative, 0.2. And remember last time when we did it before, we multiplied this by the ratio SDY over SDX, right? So that moved the decimal, that's just by 0.5 over 5, and we got negative 0.02. So put a negative in there, that's a typo, just by the luck of the draw. So that's what we always do with any significance test. You assume the null, and then you look at this test statistic. Each time you do it, you're going to get a different sample slope. And so we want to see just how likely it is that we get one this far away from 0. All right? And so we have to look at the sampling distribution of the F ratio under the null to answer these same questions that we did with T. So now, F ratio follows an F curve with degrees of freedom in the numerator and the denominator. Okay? So we've got the F right here. We're going to look at an F table, and our F stat, we're going to look at a curve that has degrees of freedom in the numerator, p minus 1, and degrees of freedom in the denominator of 23. Okay, that's what we're going to do. And we're going to look at, we got this F of 0.96, so we should look at the critical value on this curve. And I'll show it to you. Let's do it, and then we'll look on the computer. So let's look at the critical value at what? At alpha equals 0.05 at 5%. Okay, so let's do that. Where is it? Okay, so you see these F tables are going to be, they're kind of complicated to look at because they have two sets of degrees of freedom. So I'm on page 237 in your book. So you might want to go to page 237 in your book, and then you'll see, okay, what to do here. So these are for alpha equals 0.05. This is just for 5%. So the degrees of freedom in the numerator, this is in the numerator here, the group degrees of freedom. So this is degrees of freedom 1, and here's our error degrees of freedom. Those will be degrees of freedom in the denominator 2. Now we had P equals, we have 1 degree of freedom here, so we're in this column. So for simple regression with one slope, we're going to be in this column. If we add another slope, we'll be here, etc. So we're in this column, and we have 25 minus 2, 23 degrees of freedom. So right here, you can see, is the critical value, 4.279. That's our critical value. So if we got a F bigger than that, we'll reject the null. Now the F curve, I think I have a better picture of it here in your notes. I should. Let's just look. Yeah, on page 134. That's a much better picture. Okay? So it explains it a little bit better here on page 134 in your notes. So we're looking here at 1 degree of freedom and 23. We don't quite have that. We saw it somewhere, but when we looked exactly, it was 4.279. Okay? Somewhere between 20 and 30. If you just had this table, I would go with the smaller degrees of freedom, and you'd use this critical value. And you can see they're asymmetrical, these curves. very asymmetrical. Let me show it to you again. Let me show it to you. I think you'd better get it. Let's get the actual p-value on the p-value calculator. Let's just write this down first so we don't forget it. We got 4.279. So what's our actual p-value? So right now, let's look at what the curve looks like. So we'll go over to our p-value calculator here, and let's see. Get rid of this for a second. Okay, so you can go, here's our usual calculator. Now we're going to the F distribution. And we have 1 degree of freedom here in the numerator. And we said we had 23 in the denominator. And we got a statistic of, what was it, 0.96. Right, and we want to compute a p-value. Now, first of all, look at this curve. This is actually the curve, the square of the t. So t squared, if you think about, we did this with chi-squared and z. Remember, chi-squared was z squared. So if you squared the t, you're going to get all positive values. Anything between 1 and -1 on the t is going to get, you know, the closer it is to any fraction between, when you square it, it's going to get smaller, but it's all going to be positive. So we'll go up here, right? And it's very asymmetrical. And we said that we got a value, so our p-value right here is 33.74. About 34% of the curve is on this side. But what's the critical value? That would be, the critical value is when our p-value is 5%, so 0.05, and then you can compute the F. That's where that 4.279 came from in the table. That's the 5% mark. Okay? Now this F curve is going to look a lot, it's going to start getting symmetrical, and when you have, you know, really large n. So let's just add a few zeros here. Let's just add a few zeros here. And now it's going to look very symmetrical. And if you compute like the middle, it's going to be about 1. Watch. I'm saying 50% will be on about either side. Let's see. Yeah. So this is what it looks like in the mean of the F. When the null is true and you have no model, the model's just like the error, the ratio of those two is 1. So the expected value of the mean of the F distribution, it's centered at 1 and symmetrical once you get large n. Okay? So that's the idea. But you know, and more parameters. All right, so let's go back to our document camera and write some of that down. All right, so we found the actual p-value was 33.79%. And let's just draw a picture because you're not used to these. So let's look, it's all positive. Find the, so let's just do what we did here. So this is our F curve. This is just a sketch of it. It's all positive here. And we said the mean, it's 0, the mean's centered at 1, 2, 3, 4, etc. All right, so 1, 2, 3, 4, 5. All right, now it's very, it goes way up here, like this. Then it goes way out, and by the time we got to what? Our critical value, by the time we got here, that's this. That's our F star. We only had 5%, so this right here is 5%. But our actual F statistic was this. our actual F was equal to 0.96. And this, from here all the way to there, is 33.79%. Now that's about the middle. I mean, it's not 50% because it's completely asymmetrical. So of course, it's very asymmetrical, so it's not going to be centered at 50%. But this is what we'd expect when the null is true. So we got just about what we expect when the null is true. So that means that that little slope could easily be due to chance. Hold on one second. I just want to fill this in a little bit more to make sure you understand what's going on. So this was almost 1. So this whole thing, that's our p-value here. And now we're going to compare this to the p-value we got from the t-test. So let's just go back to where that was. That was on our previous page 123. I just want to show you that. So on page 123 from the t-test, we got this p-value right here. And what we got was equivalent to a two-sided one. So our F statistic, the p-value, is twice that. So let's write that down. And when we do this on the next page, we're going to do this all on the next page. So I'll show you. But for now, let's just write down, how does it compare? So our p-value for let's write this down. Our p-value for the F is equivalent to the p-value for the t. For two-sided, both, because it doesn't distinguish between the negatives and the positive. Okay? And what we got here was, we'll draw it on the next page and you'll see. It's just twice what we got for the t. Now you had a question.
Yeah, so like reject the null or not reject the null, we're looking at the p-values, so what, like...
Okay, so to reject, let's write that down. Good question. So what are we going to do? So to reject the null or not to reject the null, we have to compare, we're going to compare RF, so right here. So to make our conclusion, we'll compare RF, which was equal to 0.96. And if it's less than, we're not going to reject the null. If it was greater, if it was on this side, we'd have less than 5%. Our F was only about 1. We'd have to get an F statistic way over here to get less than 5%. Do you see that? Our F was right here. And we'd expect it to be about right there. But we'd have to go really far and get more evidence. So our F was less than F star, which was equal to from the table, 4.279. So that means that our p-value, so our p is greater. The p is like the tiny little bit out on the tail. We're way over here. So our p is greater than 5%. So we do not reject the null. We're very consistent with the model that the null says that nothing's going on. This is where we'd expect to be. Does that help? So do not reject the null. So cannot reject null. Cannot reject. Okay, I'll put it up here. The conclusion is cannot reject null, and we'll look at it again. Cannot reject null. P, in other words, it looks like beta 1 is equal to 0. It looks like R is equal to 0. It looks like there's no correlation between drinking and GPA from this data. Maybe if we got a bigger sample, we could prove it. But right now, it looks like it could just be due to chance. Does that make sense? Because the null says there's nothing going on, and we'd expect to get about here when there's nothing going on. So is that enough? Do you want me to? You'll understand it better when we turn the next page, because we're going to draw it. All right. So first of all, there's using r squared without filling out the table. You could just do exactly the same thing just by r squared and n. So I just want to show you this. So for simple regression, the mean square model over the mean square error simplifies to that. Maybe I should write it a better way for you. Let's just write it over here. I don't think that's very clear. Let's do this. Okay, so the mean square model over the mean square error is equal to what? Well, this is just SSM divided by its degrees of freedom, p minus 1, over this is SSE divided by its degrees of freedom, which was n minus p. So what's SSM and what's SSE? Remember, SSM is just r squared times SST, and SSE is 1 minus r squared times SST. And these SSTs cancel out. So we just have r squared over 1 minus r squared. Now this one's divided by p minus 1, and this one's divided by n minus p. So it's the same thing, simplifying it to n minus p over p minus 1. That's how we got that. Okay? So in other words, if we went over here, we sort of did a lot of work for nothing, really, once we know r squared, because we took this, SSM over SST, and the SSTs cancel out. This cancels out so this is the same thing as writing it this way. You'll get the same answer as 0.04 r squared over 1 minus r squared times 23 over 1. That's exactly the same thing. We did a lot of algebra, and if you do this, you'll get the same thing. That's all I'm saying. Because these SSTs cancel out. You have a 620, you're multiplying, they're in the numerator and the denominator. And then that's what you have. All right, so now we know that. And now it's easier to see how it matches up with t squared. Because remember what t was. It was SD, it was r over the square root of 1 minus r squared times, well, it simplified to this. Do you remember that? And then z was, do you remember this? Does that look familiar? That was just when we did I'll show you. That's what we did back here. Remember? That's the same thing. See? So when you square that, this is on page 123, this is the same example I'm doing now. The same example. It's exactly the same thing. So if we square this, t squared, we'll get df, 0.96. Because look, if you square this statistic, you get r squared over 1 minus this should have a square root here, sorry. It does down here, sorry. So if you square that, you'll get r squared over 1 minus r squared times n minus 2. All right, so now let's do that. So let's just do the same thing. So the relationship between, first of all, are there any questions? I know this is a lot to process right now, but we're going to be doing it a whole lot, and it will come together. So this, all right. So in other words, what I'm saying here is that for simple regression, f simplifies to the t-stat squared. So we have the f stat with degrees of freedom, with just 1 degree of freedom, that's p is equal to 2 is 1 degree of freedom, and n minus p, n minus 2 in the denominator, that's going to be the same thing as t squared with n minus 2 degrees of freedom. See, these degrees of freedom are the same. And, t doesn't have any other parameters because you can't apply it to multiple regression. You can just use it with one slope. But this, we're going to change that. So when there's just one slope, these two are the same. Obviously, they're not going to be the same anymore if we add multiple slopes. All right? And here what I'm saying is the relationship between f and chi-squared is analogous to the relationship between t and z. The f-stat yields more precise p-values for small n, but this difference becomes negligible as the sample size increases. You can look at this site. You could also look at, let's see, summary. All right, so let's go to the summary that I wrote, which is on, I think it's a good time to look at it now, to look at this relationship, to sort of summarize what we've been doing here and to understand it. So let's go to page 133 here, and let's look at this. So this, what are we doing here? So this ANOVA is used to test whether some observed effect that fits our model is too big to be reasonably explained by the null that says the effect is just due to chance. So what we're doing is we're splitting up this variance of the y's. It consists of random noise and maybe some signal that can be fit by our model. So there's noise for sure, and then there's some signal we're going to fit with our model. So we're splitting up this variability into two pieces. The part that's pure noise, just pure error, and the part that is noise and maybe has a signal in it. Maybe the null says that this is all noise too. The null says that there's no signal, no slope, and this is all noise too, that they're both noise. So that when we look at their ratios tweaked by their degrees of freedom, adjusted by that, we're just going to get 1 when the null's true. We'll expect to get 1 because the null says this model doesn't have anything in it. It's just noise too. And we think, if we reject the null, we say, no, we think there's a signal there. We think it's bigger than 1. We think the ratio of mean square model to mean square error is bigger than 1. And it's enough bigger than 1 that we think the chance of getting that just by the luck of the draw is less than some significance level that we set, like less than 5%. So that's all we're doing. We're basically, it's the ratio of two variances, really. We're using the sum of squares error to estimate the size of the noise, This tells us whether SSM could plausibly just come from noise or whether it's too big, and there's almost certainly a signal to it. Okay. From the ANOVA, we get this test statistic that's the ratio of two estimates of the variance of y under the null hypothesis. Because under the null hypothesis, it says that SSM is all noise too. So they're just two different estimates of the variance of y. That's all it is. And they should be the same when the null's true. When the null's not true, then you're going to get a lot more. Okay, so the mean of the F ratio, this is what we just talked about, when the null is true, is 1, since the null says that they're both noise. Okay. Now, and this is what the F statistic is. Right here. It's the ratios of these two divided by their degrees of freedom. And this makes the F centered at 1, okay? When the null is true. Now, both R squared and F assess the fit of a model. And here's how they're related, and here's how they connect to chi-squared. So this is what we just talked about. This measures the strength of the model. This measures the strength. This R squared is the correlation coefficient squared. So in R, it's like little r squared for simple regression. So now, so this part right here, this ratio, the correlation coefficient squared over 1 minus r squared, is central to both f and chi-squared statistics, okay? It's the central. For f, after you divide, tweaking the degrees of freedom, you get this, right? You divide each by its degrees of freedom, and we get that. And then for large N, okay, so here's chi-squared. They look the same. They look just the same, except they're slightly different. They're off by a factor of p minus 1. And basically, this is just shifted over. When the null is true, we said the f has a mean of 1. But when the null is true, the chi-squared, which is going to be the same curve, as n gets large, will have a mean of p minus 1 because we don't divide by p minus 1. And that's just arbitrary. That's just because the guy who Fisher developed the f, and he did a really cool thing by dividing through by p minus 1. He has it centered at its degrees. He has it centered right at 1. And the guy who did this, called Fisher, who invented the chi-squared, he didn't do that. So his is centered at its degrees of freedom. But for large n, I should say this. Okay, so as n goes to infinity, right, what do we know? We know that t starts looking very much like z, right? And the same thing applies with as n goes to infinity, f looks like the chi-squared. Except for, it's just the same curve but shifted over. So f is centered, but f, as you saw, is centered at 1, and chi-squared is centered at its degrees of freedom, which is p minus 1. Its degrees of freedom. That's all I'm saying. So they have the same relationship. So let's look, now that you know that, let's go back and finish up the chapter. Okay, and do another example. All right. So now we're back on page 130. And so let's repeat this using chi-squared instead of the f. Okay, so if we wanted to use chi-squared instead of the f, what would we do? We'd say, remember what we're doing here. We have r equals negative 0.2, and we have n equals 25. And that's all we really need for doing these examples. Once you know these two things, you really don't need to do that whole analysis of variance table. But anyway, for chi-squared, what are we going to do? We'll just take r squared, which is 0.04, over 1 minus r squared, which is, what is that? 0.96 times 25. And we get 104. Okay? If we wanted to do f, what would we do? So f, we just do the same thing, 0.04 over 0.96. That part's the same. But then we're going to multiply by, instead of 25, we have to subtract 2 off, 2 parameters. So we multiply by 23. And here, p minus 1 is 1. So that's the same. And that's where we get the 0.96. Okay. Now, so now this chi-squared has degrees of freedom too, but only has one set of degrees of freedom. It doesn't care. It doesn't make that adjustment for n. It doesn't, tweak the n. It just says, okay, how many degrees of freedom it has is how many groups. We've seen this before. Number of groups minus 1, or the number of parameters minus 1. The number of categories minus 1. You've already seen that the chi-squared has degrees of freedom. Now it's just the same thing. The number of, before it was the number of categories minus 1, here it's the number of parameters minus 1, same difference. So that's what we're saying. So the degrees of freedom equals p minus 1. And so here it's 2 minus 1, which is equal to 1 for here. So we're going to look at the chi-squared to find the critical value of that. So we've got this. What's the critical value of chi-squared? So the critical value of chi-squared at 1 degree of freedom at alpha equals 0.05 is equal to what? So we'll just look at our chi-square table. We'll do the same thing we did with the F, but now the chi-square table is so much nicer because it just has one set of degree of freedom. So it's so much easier to read. So it's just 1 degree of freedom. And the critical value at 5% is 3.84. We'd have to get more than 3.84 to reject the null. We got a little bit less than, we're way over here. About more than 30%, similar to the F. All right, so we'll do that. So this is equal to 3.84. So again, you can say r chi-squared, which was what? R chi-squared with 1 degree of freedom is equal to 1.04, and that's less than the chi-square critical value, which is equal to 3.84. So we cannot reject the null. So our p-value is greater than 5%, so cannot reject the null. It's the same thing. Now we can find the actual one on the p-value calculator, and then I can show you how. Let's look at that. So we're going to find the actual p-value. We said it's about 30, right? A little more than 30. Let's look. So now we'll do this, and we'll go to the chi-squared. And we have 1 degree of freedom. Chi-square is 1.04. And we're going to compute the p-value, and it's 30.78. And again, you can see the critical value here. That's when we have just 5% in the tail, and we get 3.841. So we'd have to get bigger than that. Okay? And again, let's say you have 100 degrees of freedom. It's going to be, right now it's very lopsided, but it's going to be symmetrical, and it will be centered at its degrees of freedom. So we need to have 100 degrees of freedom. By then it will look symmetrical, and about half the area will be about 100 if we do more degrees of freedom. Compute the p-value. Whoops, compute the chi-square I meant to do, sorry. Compute the chi-square. It's very close. Sorry, I'm doing this. Compute the excuse me, I didn't have it right here. Compute the chi-square. See, it's the same as its degrees of freedom. I didn't need so many zeros there. Compute the chi-square. See? It's centered at its degrees of freedom, whereas the F is just is standardized, so it's centered at 1, but they're the same curve. Once you have lots of degrees of freedom. All right, so let's go back to the document camera. And any questions? Should we draw these? Let's just draw these right now. All right, so find the actual p-value. We did, and we saw that it was a little over 30. It was 30.78%. So why don't we draw a picture of all this, what I'm talking about here. So let's look. Remember, we have this t-curve. Back on page, this was on page, what was it? Let's just do this again. Here, page 124. So let's just copy these and compare them. Here's the t and the z, and then we'll square them. We'll see that we get the chi-squared and the f, and then we'll get the same, I'll match up the curves. So that's all I'm going to do is draw these two, and underneath them draw their respective f and chi-squared, and look at their statistics. All right, so we can start with the f one. So we said that, okay, so this is all on page 124. Right now we have this f statistic with 1 in 23 degrees of freedom, and I'm saying it's the same as the t-squared with 23 degrees of freedom. In other words, this f that we just got, which was 0.96, I'm saying it's the same as the t we got before, which was negative 0.98 squared, and that is. And then on page 124, you can look, that's what I'm drawing here, we have this t curve that we did before, and we got between negative, what was it, 0.98 and positive, between those two, negative and positive, we were looking at just this tail. We got on either side, we got, what was it? Let's see, I'll just do it on this side. We got 16.86% on either side. Okay, that's what we did. And then I'm saying that that is going to be the same as this F statistic, like this, where we got 0.96. That's what we got. So we have this F curve like that. And we have 1, 2, 3, 4, etc. And we said, okay, we got an F here. I'll do 0.96 right there. That was our F. And that matches up with the T. So this is F equals 0.96. And then what we had was all this here is twice that. So this is the p-value from all the way here. P equals 2 times 16.86%, which is equal to 33.74 with rounding. It really should be 2 there, but it's with rounding. It should be exactly the same. It's just that I rounded one of them. Okay, so it's exactly the same. So that's the idea there. And then we had the F star, just to make it more clear, we had this F star back here, and that was equal to 4.28. So that's how it matches up. We squared the 0.96. We squared the 0.98 and we get the 0.96. And then we put these two tails together and we get that area. Questions on that? So now we can do the same thing. Let's do the same thing here with the chi-squared. So what I'm saying here is our chi-squared we got was 1.04. That's 1 degree of freedom. That's the same thing as the z-squared. And in our case, a z-squared equal to what? Well, let's just make it totally symmetrical. I'm sorry. Just make it look exactly the same. Okay, chi-squared is z-squared, and f is t-squared. Okay? And there's no degrees of freedom here. And in our case, just to make it look the same way, we got what? 1.04, and that was equal to whatever we got as our z-squared, which was what? Our negative, we're going to do this one, negative 1.02 squared. Okay? So that's equal to negative 1.02 squared. And now we'll draw the picture from before. And now it's the z-curve. It's going to look really similar. And again, we've got this. We have the negative 1.02. And this, when we did this here, it was 15.39. And this, I'm not drawing it very well. It should be bigger tails, but this is 15.39% for each of them, right? When I square it, I get the chi-squared, and that should be, the p-value should be twice that. And it will look very asymmetrical too. It's going to look really, we got twice that, and that's right here. That's our chi-squared that we got 1.04. And this whole thing here that we got, that whole thing was a p-value equal to twice that, 2 times 15.39%, and it was equal to 30.78%. And that's the idea. Oh, and then we got this little way out here. We had our critical value. We didn't reach it. Our critical value was 3.84. And after that, it's 5%. It's a small amount. So that's the idea. Any questions on that? This is between this is 1.02. So here, 1.02 and negative 1.02 in terms of z's. And this was 0.98 and negative 0.98. This is the t curve and this is the z curve. And then when you square that, you get your chi-square statistic. And when you square this one, either one, you get that. Okay, so that's the idea. Now, remember that chi-square is defined as the sum of independent z squareds. So that shouldn't surprise you. That's not the definition of the f, but it so happens with just one degree of freedom, when you have simple, just one parameter like this, the t squared is the f. So it's a very analogous role they play. In both cases, what's going on is that extra degree of freedom, that set of degree of freedom for the t, you know what it is. It's because you don't know the standard error. You don't know those errors in the whole population, the standard deviation, right, of the population. You're making an estimate. And so you have to, for mean, you subtract off 1 degree of freedom. For line, you subtract off 2. Once we get into more, it's n minus p. Same with f. That's the difference between the f and the chi-squared, is that the chi-squared is not making an estimate of, just like the z is not making an estimate of the standard deviation of the model. So it's not doing that tweak. It doesn't have, the chi-square doesn't have any degrees of freedom associated with making an estimate of the standard deviation. Neither does the z. So they're very analogous. Okay? All right. It's a lot to digest, but we're going to be doing this throughout. This is how we're going to be assessing the fit of linear models in general. We're going to use, this is one of the techniques to do it. We're going to look at other techniques, but this is a very common one to do it with this analysis of variance. All right. So now let's put it all together, and this will help you do your homework now that we understand it a little better. So let's look at the next page. But meanwhile, I should do While we're taking a break, if you don't mind, let's just do an eye clicker and see what you remember here. So let's go here and let's just get out your eye clickers and see what you remember. Okay, so let's do this. Okay, I'm going to stop it pretty soon. The chi-square, we're talking about the chi-square here. Okay, let's stop that. Just pick something, and let's see what you picked. It should be D, right? Good. E? There wasn't even an E. Sorry, you make me laugh. All right. Now let's just go up one. I think I had another question here. How about for the F? Let's just do the same thing. Now you should get it. I'll give you a big hint. The answer is not E. Okay, let's stop it pretty soon, so just answer. Okay. And let's see. So the answer should be what? B, right? Great. Okay, now let's see if there's, let's do another one. Okay. All right, you all done? Everybody get a chance? Let's stop it, and the answer should be A, right? Oh, no. That's for the chi-squared. The F, remember, is centered at 1. Centered at 1. The F has expected values 1 always. Okay? P minus 1 would be for the chi-square, be its degrees of freedom. Okay, we're talking about the F. Now let's go back to the document camera. And all right, so let's look at this example. So now, here's from our homework and final data from 107 students. All right, and so imagine these 107 students were chosen, or random sample, from a much wider population. Otherwise, there's no point in doing, if this was the whole population, we really have all the data, and this correlation is the correlation of what we have for the whole population. So we're looking at some imaginary larger population of all, let's say 2,000 Stat 100 students, and the null is that in those 2,000, when we're predicting homework, we're predicting finals from homework, okay? And we're saying the null is that there's no relation, which would be kind of, actually in some classes there isn't, not in statistics usually, but sometimes they assign homework that doesn't really help you with the exams and there's not much correlation. I hope that's not the case here. But this would be the null that homework does not help you. So no matter how low or how high your homework is, your best estimate would just be the average homework score, and that your slope would be 0. That's the same thing as saying rho, which is R, rho for the whole population is 0. That's the same as that. Those two things are equivalent. And what this is our null scatter plot, our null model, or scatter plot that's under the null for whole population. And it's always the whole population, so that's all 2,000 students. Then we have this sample, this is what we see, and we get this R, not 0, and we want to know if that's big enough to reflect a real signal in this population, or if that's consistent with an R equals 0 in the population. All right, so what are we going to do? So we need this. We also need to know this. And to fill out this chart, first of all, just to fill out this chart, we also need, the SST. All right, so let's look at this. So use R and SDY to compute this, all right? So R squared is going to be 0.4 squared. And SST, do you remember that? That's just N times SDY squared. So that's going to be our 107 times 10.3 squared. And this is a big number. This is 11,351.63. And that's what we put down here if we want to fill out this chart. Okay. So let's do that. 11,351.63. Now we're going to break that up into two parts. The parts that's due to the model, all we're doing is we're saying R squared times SST plus 1 minus R squared times SST is equal to 1 SST. R squared plus 1 minus R squared, of course, has to equal to all of it. Okay? So the R squared is, now we're doing 0.16 times that, times 11,351.63, and that's going to give us our sum of squares model, which is 1816. Boy, I can't even read my handwriting. 1816 times 0.26. All right. I didn't want to have to do all these calculations in real time here, of course. And this one is going to be 1 minus. So what should it be? 0.16, so it has to be 0.84, right? Those 1 minus R squared. And it's times the same business, times SST, 11,351.63. And then, of course, you could subtract that from that and get the same thing, because and then you get 9,535.37. All right, now the degrees of freedom, you should know this. This is n minus 1 here, right? So that's going to be 107 minus 1, that's 106. This one's really easy. We have one slope. This is really your number of slopes here. It's P, 2 parameters. It's P minus 1. For simple regression, this is always going to be with one. This is really the number of slopes. It's P minus 1 minus the intercept. So this is 2 minus 1. So this is 1. And then this has to add up, so you know it's 105. But in general, it's n minus p. They have to add up to 106. And they do. And then you're just going to take the mean squares. So you have your 16.26 divided by 1. And here you have 9,535.37. 135.37 divided by 105. And I got 90.813. Okay. Now you take the ratio of those two, and it's 1816.26 divided by 90.813, and I got 20. All right. Now, this is the square. See that this is the root mean square error? The square root of the mean of the squared errors. That should look really familiar to you. That's like the root mean square error. Square root mean square error. So it's the square root of, you see there's the square root of the 1 minus r squared. And this is like the standard deviation of the y, of the errors. Right here, of the y. Anyways, so this right here is the square root of 90, square root of this, 90.813, which is equal to 9.53. Now, that's the same thing as the standard, let's look at this. So this is the same thing as the standard deviation of the errors. This right here is the standard deviation of the errors. It's the standard deviation plus of the errors. That's 9.53. Okay? It's the same thing as, so the standard deviation plus of the errors, maybe I should write this down, is going to be what? It's going to be 107 over 105 times the standard deviation of the errors without the plus. You see, what we're doing is we're dividing by 105 instead of dividing by 107. If we divided by 107 here, we would have gotten the standard deviation of the errors. So once you get, so it's, okay? I think in your homework, you're going to have to go the other direction. So you'd say 105 over 107. In general, the SD plus of the errors is going to be n over n minus p times the SD of the errors. All right, so we've done that much. I'm just concentrating. This is just one question on your homework. That's why I'm focusing a little bit on it. But you can see you divided by 105. If we had divided by 107 here, and then taken the square root, then we would have gotten our standard deviation of the errors. All right, so our conclusion, what is our conclusion? That f with 1 degree of freedom in the numerator and 105 was equal to 20, and that's much greater than f star with 1 and 105. And if f star was equal to 4 using the table. Okay, so I just also want to show you something that you could have done this whole thing much easier. Like you didn't really have to, if I didn't ask you to fill out the table and you knew the same information, you could have said using that f is equal to r squared over 1 minus r squared times n minus p over p minus 1. Look what you could have done. You could have just said 0.16 over 0.84. It's really the same thing times 105 over 1, and that's 20, and that's much easier to do. So you could have done it that way. Now, let's see. Now let's do, are we going to reject the null? This is much greater. So yes, we're going to reject the null. So reject the null big time. Because look what it's going to look like. We've got 20 and 4. We'd expect 1, 2, 3, 4, This is, okay, so this is, it's going to look like, and 4 is F star. RF, which means 5% is this way. RF is 20, which means almost 0% is this way. That's RF. This is going to be a p-value of, this way it's almost 0. Do you want to see what it is? We could look. I looked and it was, I got a p-value of just, okay, so this is using table. Using p-value calculator, I'd already looked. We got a p equal to 0.001967%. So it's almost 0. That's what this is. That's what that p is. I said almost 0 there, it's that. All right, now let's do the same thing using chi-squared. So how's chi-squared going to be different? We're going to say r squared over 1 minus r squared times n, and that's it. That's so easy. So we'll do the same thing, 0.16 over 0.84, and instead of over times 105, we're just going to make it a times 107, and you get 20.38. And then, so r chi-squared with 1 degree of freedom is equal to 20.38, and it's going to be much, much bigger than chi-squared star with 1 degree of freedom, which is, we looked before, 3.84. That's at alpha equals 0.05. So using the table, that's at 5%, see? So we'd have, so in general, so we'd reject the null. Now, one other thing is you could say, what if I wanted z then? You could say, okay, z is equal to the square root of chi-squared. So it would be the square root of 20.38, which would be equal to 4.514. Okay? And note, we'll write that too, here, that t is equal to the square root of f. So it would be equal to the square root of 20, which is 4.472. Now, one last thing that I want to show you, and that's on the next page. You're going to be doing, you have 4 statistics. This is, you're going to be filling out a chart like this on your homework. You have 4 statistics that test the same thing for simple regression. They all test the same thing. Okay? And so it's easiest probably, so to find the p-value, you can either do a one tail or both tails on the normal curve, depending on the alternative. So for both this one, for these two both, you can use the one-sided if your alternative is greater than or less than, and two-sided if the alternative is not equal to 0 for those two. And I think it's easiest for both of these, like if you want to fill out a chart with all of them, I think it's easiest to compute the chi-squared and the f and then take their square roots. So that's pretty much it. And so you'll do a homework like that, fill out a chart like that. Okay, so that was a lot to digest, I know, but